Welcome back, students. In this video, I'm going to show you how to model sequential circuits in Verilog. Here's the outline of this presentation. I'm going to show you how to model latches and flip-flops. I will cover blocking versus non-blocking procedural assignments. I'll show you how to model sequential circuit diagrams, how to write test benches for sequential circuits, how to model Mealy and Moore state diagrams, and finally how to model registers and counters. Let us recall the always statement. Okay, so the always statement is a very important statement in Verilog. So it starts with the always keyword. This is the syntax as shown here, followed by the @ symbol, okay, and then we have a sensitivity list between parentheses. So this sensitivity list is a list of signals, okay, as shown here, signal 1, signal 2. You can actually have any number of signals enclosed between parentheses and separated by commas. So we say that the always block, the block here is surrounded by begin and end, and it can include any number of procedural statements. So the statements that are written inside always are procedural statements. And as long as you have more than one procedural statement, you have to enclose them between begin and end. If there is only one statement, then there is no need for begin and end. Now, the meaning of the sensitivity list is very important because the always is sensitive to this list of signals. It means that if there is any change in value in any listed signal, then it's going to trigger the execution of the always block. So the procedural statements are going to be executed until we reach the end, and the always statement is going to watch these signals. If there is any change in any listed in the value of any listed signal, then this is going to trigger the execution of the always block. So this is the meaning of the sensitivity list of the always block. There are some important guidelines for the sensitivity list. In the case of a combinational logic, the sensitivity list must include all the signals that are read inside the always block. So any signal that you read inside the always block must be listed in the sensitivity list. Now, there is a simple way to define this list by writing @ between parentheses, or just @ even without parentheses. So both syntaxes are acceptable. So the compiler will recognize that you are modeling a combinational logic and is going to replace the star with all the signals that are used, that are read inside the always block. Now, this is for combinational logic. In the case of sequential logic, okay, the sensitivity list may not include all the signals that are read inside the always block. So you might actually list some of them, but not necessarily all of them. This is a major difference between modeling a sequential logic and a combinational logic. Now, in the case of edge-triggered flip-flops and sequential logic, okay, then we can use the keywords positive edge and negative edge. So positive edge of a signal means that this is when the signal changes from 0 to 1. So only at the positive edge of the signal, okay, then you are triggering the execution of the always statement. So when you use this keyword, this means that the always statement should be triggered, it should be executed only at the positive edge of the signal. For example, you can use a clock. Similarly, when you use the negative edge, this is also another important keyword. It means that you would like to trigger the execution of the always statement at the negative edge of the signal, which means that the signal is going to drop from 1 down to 0. This is the meaning of the negative edge. So when you use these keywords in the sensitivity list, it means that you would like to trigger the execution at the edge of the clock. It could be the positive edge or the negative edge, depending, of course, on your circuit. Now, let us have a look at this slide, how to model a D latch with enable. So I would like to write a module, okay, and this module is called D latch. This is the name of my module. It has two inputs, the D input, this is my data input, and also it has an enable input. So I can use here enable, for example, as a clock, and the output here is called Q. So that's my output. There's only one output, which is a Q. Now I'm going to write an always statement, and this always statement is sensitive to the D input as well as to enable. So both signals here are listed in the sensitivity list. So if enable, it means that if enable is 1, that's what's the meaning of this if statement, then we assign, then Q becomes D. Okay, so this is called a non-blocking assignment operator. Notice the symbol here. It's called a non-blocking assignment operator. I will cover this assignment operator in details in the next few slides. It's called non-blocking. So we use this non-blocking assignment when we are modeling latches or flip-flops or even sequential circuits. So it means that if this enable is true, then the value of a Q becomes the value of the D input. Otherwise, there is no else part, because if enable equal to 0, we do not change the value of a Q. So for this reason, there is no else. Okay, so it means that if enable equal to 0, do not change the value of Q. So the value of a Q will be unchanged if enable is equal to 0. Now notice that Q appears inside the always statement, and because it is used inside the always statement and it appears on the left-hand side of a procedural assignment, then in this case the register here type must be used for the output Q. So it indicates that the output Q must be a register because a Q appears on the left-hand side of a procedural assignment. So only procedural assignments can be used inside the body of an always statement, and therefore any signal that appears on the left-hand side of a procedural assignment must be of type register. This is the meaning of this type. Okay? So that's how we model a D latch. Now, how about modeling a D-type flip-flop? In the case of a D-type flip-flop, so here it actually is my module, which is called DFF here, or D flip-flop. It has two inputs, D and clock, and it has two outputs, Q and Q bar. So these actually are my two outputs. Notice that both of them are of type register, because I'm going to define their values inside the always block, and therefore they appear on the left-hand side of a procedural assignment, so therefore they must be of type register. I'm going to write an always statement. This always statement is sensitive to the positive edge of the clock. Now notice that D does not really appear, although D is an input, it does not appear in the sensitivity list. And the reason why the always statement is not sensitive to D, so even though there might be changes in D, there is no change in the output Q. So the output Q is going to change only at the positive edge of the clock, and this is why only the positive edge of the clock appears in the sensitivity list of this always statement. So at the positive edge, when the clock goes from 0 to 1, this is the rising edge of the clock, we are going to change the value of a Q becomes D, and the value of a Q bar becomes not D. Okay. Now notice that these two assignments here are non-blocking assignments, indicating that these two assignments will take care in parallel at the same time. So the value of a Q and a Q bar will be D and not D at the same time. This is the meaning of the non-blocking assignment. I will actually have more explanation between blocking and non-blocking assignment in the next few slides. Just wait actually for a few slides and I will go into the details. Now, if I would like to model a negative edge D-type flip-flop, Okay, so I only have to change here the keyword from positive edge to negative edge. This is very simple. So we can use the negative edge of the clock. So therefore, we trigger the execution of the always statement at the negative edge of the clock. So at the negative edge, the value of a Q becomes D, and the value of a Q bar becomes not D. Okay, remember that these are called non-blocking assignments. These are procedural assignments, and therefore Q and Q bar, okay, must be of type register. Okay, because we can only assign to a register, okay, when we are using a procedural assignment inside the always block. So here's an example of a negative edge triggered, okay, it's a negative edge triggered D-type flip-flop. Now we can actually add a reset input. Now this reset input can be synchronous or asynchronous. So we have two different types of resets. Okay, so the meaning of a synchronous reset, if the reset is synchronous, it means that the reset will take place at the edge of the clock. So we are going to synchronize the reset with the clock. So here's actually another module which is called D flip-flop 3. So now we are seeing different D flip-flops. There are three inputs, D, we have a clock, and also we have reset. So these are the three inputs to the D flip-flop. We have two outputs, Q and Q bar. So the reset now is a third input to this D flip-flop. So again, at the positive edge of the clock, okay, so this is a positive edge triggered D flip-flop. We check the value of reset. So I'm going to write an if statement inside always. So if reset, it means if reset is true, is equal to 1, then Q and the Q bar will be 0 and 1. So we're going to reset the value of a Q. So Q becomes 0 and the Q bar becomes 1. We can do this in one assignment. I can actually assign to both outputs Q and the Q bar. So I can actually use the concatenation operator and assign 2 bits at the same time to both outputs, Q and Q bar. Else, if you are not really resetting, then Q becomes D and the Q bar becomes not D. Again, I can do this in one assignment, okay, by using the concatenation operator. So the concatenation operator here means these curly braces. This is the concatenation operator. I'm actually assigning to two outputs, Q and Q bar, in the same assignment statement. These are called procedural assignments, and these are non-blocking assignments. Now here is another D flip-flop that has an asynchronous reset input. So again, the inputs, we have three inputs, D, we have a clock, and we have reset. But this time, this reset is asynchronous. It means that we can reset at any time, okay, even without the presence of the clock edge. So we don't really have to wait for the clock edge. We can reset at any time. We have two outputs, Q and Q bar. Again, notice that they are of type register because we are using procedural assignment. So this means that they actually are variables because they appear on the left-hand side of a procedural assignment statement. So the always statement now is sensitive to the positive edge of the clock because we have a D flip-flop. And also it is sensitive to the positive edge of reset. In other words, if we have the positive edge of the clock, we are going to execute this always statement. If we have the positive edge of reset, we are going to also execute this if-else statement. So if there is a reset, we don't really have to wait for the positive edge of the clock. So it is sufficient to have a reset to execute the body of this always statement. So we execute this if-else if we have, let us say, a reset at the positive edge of reset. So if reset is equal to 1, if it is true, then Q becomes 0 and the Q bar becomes 1. So we can do this at the positive edge of reset without waiting for the clock. Else, if it is not reset, it must be that we have the positive edge of the clock. So either we have an event on the positive edge of the clock, so the clock goes from 0 to 1, or we have an event on reset. The reset goes from 0 to 1. If it is a reset, we reset Q and the Q bar. So Q becomes 0 and the Q bar becomes 1. We can do this in one assignment. We're assigning 2 bits here to Q and Q bar. Q will be 0 and the Q bar will be 1. Else, it means that we have the positive edge of the clock. Then in this case, Q becomes D and the Q bar becomes not D, and we are doing this again in one assignment. Okay, so this is done in one statement. So notice that in the case of asynchronous reset, the reset here must appear, the positive edge of reset appears in the sensitivity list of the always statement. Whereas if the reset is synchronous to the clock, we remove the reset from the sensitivity list of the always statement. So this is a major difference between synchronous versus asynchronous. So if it was synchronized with the clock, we should not write reset as part of the sensitivity list. This should not appear if the reset is synchronized with the clock. Only the clock, the positive edge of the clock, should appear in the sensitivity list. But because here reset is asynchronous, it is not synchronized with the clock, we have to have the positive edge of reset part of the sensitivity list. So it's very important to pay attention to the sensitivity list of the always statement. Notice that, okay, the D input is not really part of the sensitivity list. So even though we have changes in the D input, we do not execute the body of the if-else statement until we see either the positive edge of the clock or the positive edge of reset. Okay, so you can see that here the D input does not appear in the sensitivity list because the always, okay, you can see that this D flip-flop is not sensitive to the D input. So now we have seen 2 different types of assignments. Okay, in a previous presentation I talked about the blocking assignment, and in this presentation we have seen the non-blocking assignment. So let me talk about these 2 different types of procedural assignments. So both of them are procedural assignments, and you can use them inside the always block. So the blocking assignment has the following syntax. You can write variable, and then you have here the assignment operator, and you have expression. So this is the syntax of a blocking assignment. So Verilog defines this assignment operator as the blocking assignment. Okay, so this is very similar to what you have in high-level programming languages. This is the assignment operator, which is used in assignment statements. So what it means is that we have to update this variable that appears on the left-hand side of this assignment operator before we move to the next statement. So basically the statements that are written inside the always block are procedural and they are executed sequentially. So we update if the assignment operator is a blocking assignment operator, then the variable that appears to the left-hand side of this assignment operator must be updated before we move to the next statement. This is the meaning of blocking assignment. It's very similar. Okay, it has exactly the same meaning as the assignment statement, which is used in a high-level programming language. On the other hand, we have the non-blocking assignment that we have seen, okay, when defining, for example, let us say flip-flops or latches. We have seen the non-blocking assignment, and it has the following syntax: variable, and we have the non-blocking assignment operator. You can see that it has different syntax, and then we have expression. Okay, so this is the syntax of the non-blocking assignment. So the difference is only in the assignment operator. So we have a different operator for non-blocking assignment. So you can, just from the syntax, you can tell if the assignment operator is a blocking or non-blocking. So really, what's the difference between the two? Why do we have these 2 different assignment operators in Verilog? I'm going to address this question in the next few slides. Hopefully this will become very clear, okay, at the end of this presentation. So in the case of non-blocking assignment, okay, it means that the variable is updated not immediately, but at the end of the procedural block. This is a major difference between the blocking versus non-blocking assignments. So we don't update the variable that appears on the left-hand side immediately. We wait until we reach the end, okay, of the procedural block. So the update will happen at the end of the procedural block. So why people have invented, okay, why the designers of the Verilog hardware description language have introduced this non-blocking assignment? Isn't that a bit confusing? Well, let us see why we need this non-blocking assignment. It's very important for sequential circuits, and I'm going to clarify this in the next few slides. Okay, so here's an example of blocking versus non-blocking assignment. Now let us take a look here, okay, at this module which is called non-blocking. And in this module we have the input here which is in. That's my input to the sequential circuit. So we have here 3 D flip-flops, and we have a clock. Clock here is connected to the clock input of all of these D flip-flops. And only we have here one output which is out here, which is the output of the last D flip-flop. This is an example of a shift register. I'll talk about shift registers in great details in a later presentation. This is just a simple sequential circuit that has 3 D flip-flops connected in this way. Now inside this module, I'm defining here Q1 and Q2. Notice that the type here is register. And I'm writing an always statement which is positive. It is actually, sensitive to the positive edge of the clock. You can see that from the sensitivity list. We are using here the positive edge keyword. So therefore, we trigger the execution of this always statement at the positive edge of the clock. Now here, notice that Q2 becomes in, Q1 becomes Q2, and out becomes Q1. Now, because we are using here the non-blocking assignment operator, it means that we don't assign immediately. We wait until we have reached the end of the always block. So when we reach the end of the always block, we read in Q2 and Q1, and we do this assignment in parallel at the same time. So these 3 assignments are done in parallel. So it's not they are done sequentially. We finish one before moving to the next one. No, we are doing them in parallel. So therefore, Q2 becomes in, Q1 becomes Q2, and out becomes Q1 at the same time, as indicated above, okay, in this circuit diagram. So Q2 becomes in, Q1 becomes Q2, and out becomes Q1. This is the meaning of non-blocking assignment. On the other hand, if I use blocking assignment, if I change the assignment from non-blocking to blocking, okay, as shown here on the right-hand side, okay, so if I change the assignment operator, okay, to blocking, it means that first we have to assign into Q2, so Q2 becomes in, and then Q1 becomes Q2, which is also in, and out becomes Q1, which is also in, which means that we have eliminated the second and the third D flip-flops. So now we have, okay, we don't really have a flip-flop for Q1, and we don't really have a flip-flop for out. We just replace them with a wire. So therefore, the value of a Q1 and out are simply the same thing as the value of a Q2, which is in. So at the rising edge of the clock, at the positive edge of the clock, this is what will happen. Okay, Q2 becomes in. Okay, so first we assign to Q2, which is the value of in. And then after we finish this assignment, then we assign to Q1 the value of a Q2, which is also in. And then after finishing the second assignment, then we assign to out the value of a Q1, which is also in. So therefore, basically Q2, okay, and Q1 and out, they will all become the value of in, and therefore this will eliminate the need for having here. So therefore we are dropping, we are canceling, okay, the second and the third D flip-flops. So the meaning has changed when we use a blocking assignment. So for this reason, if I don't really want to have this behavior, if I'm not really describing, if I really would like to describe a shift register, then in this case I have to use a non-blocking assignment. as shown to the left, and I should never use a blocking assignment as shown to the right. So this should not be used. So therefore, we use non-blocking assignment when we are modeling sequential logic as shown here to the left. Because if you use a blocking assignment, then therefore you are eliminating these D flip-flops and you are replacing them with just a single wire. On the other hand, if I'm modeling combinational logic, okay, let us take a look at this simple combinational logic. I have an AND gate and an OR gate. I can model this also easily with an always block. So this always block must be sensitive to all the inputs, A, B, C. Notice that there is no memory, there are no latches, okay, no flip-flops. So X becomes A and B. So if there is actually any change in the inputs A, B, or C in any signal, we trigger the execution of this always block. So the value of X becomes A and B, and the value of Y becomes X or C. Now notice that here it means that X is already A and B. So first we assign to X, and then we use the value of X, which is A and B, in the second expression. So it will be A and B or C. That will be the value of Y. So here we must use, okay, we have to use the blocking assignment because it will be wrong to use the non-blocking assignment. Suppose we use the non-blocking assignment instead. Okay, so here I'm rewriting the module, but I'm calling it non-blocking. The same inputs A, B, C, the same outputs X and Y, but I use here non-blocking assignment to assign to X and Y. This will change the meaning. It will change the circuit. This means here that we are going to do the parallel assignment at the end. So therefore, this X is not the value of X that was computed by the previous assignment, because this assignment is non-blocking. It will be the old value of X. So it's not the value of X which is computed above, it is the old value of X. So therefore we have changed the meaning of the circuit. It becomes like this. Okay, so therefore the old value of X has to be latched as shown here. So I need actually a latch to remember the old value of X. So we're going to compute here a new value of X, but we don't really use it to compute Y as indicated here. We are using the old value of X to compute Y. So changing the assignment operator from blocking to non-blocking changes the meaning of this circuit and introduces a latch. So for this reason, we never use non-blocking assignment when we are dealing with combinational circuit. So this should not be used. We should always use the blocking assignment when we are modeling combinational logic. So here are the guidelines, okay, for coding in Verilog. So when you are modeling combinational logic, use the blocking assignment. So always use the blocking assignment when you are modeling combinational logic. So blocking assignment was meant to be used with combinational logic. If you are modeling sequential logic, on the other hand, use the non-blocking assignment because it was meant specifically for sequential logic. If you would like to model both sequential and combinational logic, make sure that you understand exactly what you are doing in the same always block. Okay, then it is better to use the non-blocking assignment. But make sure that you exactly understand what you are writing in the always statement or in the always block. So use the non-blocking assignment if you would like to model both the sequential and the combinational logic. Do not mix blocking with non-blocking assignments in the same always block. You will confuse yourself and you might actually get unexpected results. Okay, if you mix blocking with non-blocking assignment in the same always block. Another rule, okay, which is shown here, the fifth rule, do not make assignments to the same variable from more than one always block. Okay, so do not do this. Do not write two different always statements or always blocks that assign to the same variable. Do not do this. Okay, it's like having wired logic. You are actually assigning to the same variable from two different blocks. Do not do something like this. So this is the end of my presentation, my video. In my next video, I will show you how to model sequential circuit diagrams and how to write test benches for sequential circuits.